Thank you very much. So good morning, everybody. Thanks for being here, and I would like also to thank the committee who gave me this opportunity. So today I will try to show you that it's possible to go towards a universal framework which describes and controls friction at the atomic scale. So what is friction? Friction is the force that opposes the movement of some objects in contact or in which they interact. This is a very general question. There's nothing to do with the size of the matter, the chemistry, the geometry of the object. It's very general, and this definition applies whatever is the nature and the size of the object. In fact, we can imagine, we can see that there are a lot of examples of kind of friction, like the astronomical scales. For example, planets feel the attraction force from the gravitational force from the other planets, so impeding their motion. Or at the Earth scale, for example, in which we have movement between tectonic plates. At the human scale, going down in the scale, we experience friction every day. Like, for example, when we try to brake our motorcycle, or we grab a statue around, maybe, or if we move our bones, so in our joints, there is also friction inside, and also, of course, in the other micro electromechanical systems. So at any scale, friction is present. We want to study friction because uncontrolled friction causes a lot of damage, where device fault, energy loss. Can you imagine what it means? I mean, we have to spend time to fix a device, we have to spend time to replace the material, we have to spend time and energy, we have to waste time to keep the movement going. So it has been estimated that if we were reducing in the whole world by 18% the friction, we could avoid the production of 290 million of tons of carbon dioxide. And also we could save 117 billion euros. So it's not, but also, controlling friction is not only to save money, energy, resources, and time, but also if we control it, we can even produce it. We can produce energy. In fact, this is one of the topics of the CTU Global Postdoc that I'm mentoring in these years, about transition, about triboelectric nanogenerators, these tank materials which can produce electricity from friction. So control friction falls in the framework of understanding and control together to predict the friction response. And this falls within the sustainable development definition. In this respect, I'm part of a panel of the European Commission, which is trying to design guidelines for a transition towards renewable energies. There are theories already, of course. Tribology is the science studying friction, wear, adhesion, lubrication, which provides already some definition of friction. The most famous one is the friction force is proportional to the load applied. So the coefficient of friction, is the one that describes the response of the system. But what if we don't have any load? So we have to take into account also the adhesion. So still, if without load, we will feel that there is still friction if we try to slide one object relative to another one. But still, this depends on the contact area, which we will see is not really defined. Also, friction depends on other parameters, so people were trying to formulate more and more complicated formulas, expressions to define friction. But the problem is that all these coefficients, all the parameterizations, depend specifically on the system and depend also on the conditions, temperature, pressure, sliding velocity, and what is worse, from the contact area. So in general, there is no universal framework available, which means that the whole theory about friction is fragmented into different equations, which case by case must be refined by means of experiments or simulations, and then we have to follow this continuous feedback to improve the theory, and finally have some kind of prediction, which still, it's kind of paradox, we have to measure it to predict it. So we need to do something. I mean, so the goal of this work is to try to find a way to predict friction only from the geometry and chemistry of the system. Let's see if we can go towards this direction. So I just say that friction is the result of the interaction or when two objects are in contact. But what does it mean that they are in contact? Think to the surface of two objects. They are in contact if in the interface there is no space. But if we zoom in, every object is made by atoms. Atoms are made by nuclei, by electrons. So here we have electrons around, which actually never touch. So there is never a real contact. So the concept even of contact area is ill-defined at these scales. So friction is the result of just interactions. And no matter the scale, it's always the result of interactions among atoms, if we look, of course, at this kind of detail. We discussed a lot of possible tribological interactions in a review which was published a few years ago. And these are just examples, but as you can see, this involves always something at the atomic scale, some process at the atomic scale. Even the presence, the interaction with external electric or electromagnetic fields, for example. So in order to account for this, in our definition, we have to include quantum mechanics. Friction transforms energy. Friction hinders the movement of an object, but this movement, I mean the kinetic energy, where does it go? It goes into heat, so it transforms ordered motion into disordered motion, from work to heat. So we have an energy dissipation. This transformation depends on the material, but we want a universal description. So another step forward is to find a transformation of this energy, which is independent of the chemistry and the geometry of the system. So in this respect, one promising way is to use phonon theory. What is a phonon? A phonon is a collective movement of atoms which oscillate at synchronous frequency. Imagine that we have some atoms distributed in the space. This atom displays towards left, this towards up, this towards down. This pattern is the geometric aspect of the phonon, which can identify with some vector E. These atoms are oscillating around equilibrium position at a certain frequency omega. These two define what is a phonon. And we have several of these possible relative displacements in the structure. So we can calculate all the possible phonon modes, all the possible phonon of the structure. Then the total displacement in general can be described as a sum of all of this, because mathematically it's defined. It's a basis. So we do a linear combination of the basis and we get the displacement, the total displacement. What if I consider as a displacement just the net relative slide of two surfaces? Still, I can write it as a linear combination. It's a particular case of a general displacement. So maybe I remove what is not necessary and I consider just, this is E2, I don't need it. And I consider just these two phonons to describe the relative motion. In this case, then I can describe the relative movement that gives rise to friction. I can define then these phonons, these specific phonons, as sliding phonons, because they describe geometrically the relative sliding. Now, dynamically, what is omega? Omega basically is a measure of the friction force. In fact, classically, each phonon is an ideal spring. So from the phonon theory, we see that each spring has associated some force constant, which is equivalent to the frequency associated to it, which is defined in this way. So phonons carry both the geometric information, the dynamic, and the dynamic information, the direction of the displacement, and the magnitude of the friction force. Then, if we lower omega, if we are able to control omega, we are able to control the friction. They are directly proportional with a square, but we lower omega, we lower the friction force, and we have easier sliding. How to control omega? Omega is defined by means of this equation. This is an eigenvalue, eigenvector equation in terms of the dynamical matrix. The dynamical matrix basically collects all the information about the chemistry, the geometry of the system, the interaction between the atoms. So it's a consequence of the definition of D that omega is a function of the interatomic force constant. These interatomic force constants can be calculated by means of quantum mechanics. So intrinsically, we can include quantum mechanics in our definition. The problem is that, I mean, this quantity is not easy. It's not an easy quantity because it's a multidimensional tensor. I mean, it's kind of complicated to really check all the details. Then it's better to use some electrodynamical descriptors to collect fragmented information into few parameters. So one possibility is to relate omega with the structural distortions, maybe by means of the group theory, or with the properties of the electronic density, like with the density of states, the bond covalency, the orbital polarization, the Bader charges, and other descriptors that are defined according to the electronic density. In this respect, we already exploited actually this kind of procedure to parameterize the interaction with electric field and with inert intercalants. I mean, by using some non-reactive molecules, like nitrogen, CO2, to modify the friction in TMD's materials. And this has been done in collaboration with my previous PhD students and within my previous GACH funding and Horizon funding. Or we have also to parameterize the atomic type. How can we parameterize the periodic table? How to associate a number to the atoms? There are a lot of ways: electronegativity, atomic number, van der Waals radius, whatever. But they are just atomic properties. We have instead to parameterize the atom within the structure, within its geometric environment. One way, then I said, okay, maybe it's better to consider the phonon density of states, and I designed the cophonicity metric, which is a way to, it's defined by means of some integral, we can discuss later if you're interested, but it's a way to associate to a couple of atoms a number. So it's a metric which parameterizes the interaction of two atoms producing certain phonon displacements. So I introduced also, okay, this word in Wikipedia just to make it more and more known, and now it's also used for other studies other than friction, like transition, ferroelectricity transition, for example, and so on. Okay, so now we have this information. How can we use it? I already mentioned my work with my previous PhD students about electric field, intercalants, but also immediately, without performing any dynamic simulation, we were able to understand what's the contribution of the bulk to the macroscopic friction in these materials. So these have lower contribution than this one, and these ones, and we obtain it without performing any dynamic simulation, which saves a lot of time, a lot of resources, and you don't need large computational centers and so on. Another possible outcome, which is, I think, really important, is we start to have some guidelines, some design rules to create a new material, new tribological material. I started from molybdenum disulfide, and following this prescription by combining omega with covalency, cophonicity, or other descriptors, I realized that if I substitute molybdenum with titanium, this compound will have less friction, will manifest less friction if we try to slide the relative layers. But also, I mean, the sliding modes do not represent only the friction, I mean, the restoring force, but they are the active part of the movement. If they are active, there is the movement. If they are not active, there is no sliding movement. So they are also part of this process. So dynamically, the sliding modes are responsible of the sliding, of the total sliding of the structure. And so the sliding is active until they own enough energy, but phonons interact. So the sliding phonons may lose energy by interaction with other phonons which have no sliding character. They recombine, and in general, the result is a third phonon which has no sliding character. So the energy, the net drift, has been transferred to a random motion, so from work to heat. So sliding phonons lose energy due to the scattering. So we have to include the scattering. Let's check if dynamically this makes sense, because for those of you who are more into the phonon theory, they may say, this is a local description. No, because it works also far from the equilibrium. And in fact, what we did, we considered a molecular dynamic simulation in which I have just 2 layers of this structure, molybdenum disulfide. The system is totally adiabatic, it's totally isolated, no thermal coupling with any thermostat, anything. So initially we kick the first layer, the top layer on the right, and then we let the system evolve. At the beginning, the 2 layers slide one on top of the other. At a certain point, they stop. So they start to just vibrate around the equilibrium position. I can show you this in just some snapshots. So as you can see from the top view, initially the 2 layers are sliding each other. Also from the lateral view, this is quite clear. But at a certain point, they start to oscillate around the equilibrium position because the sliding phonons lost the energy. Now, let's quantify this loss of energy. What we did, we considered the kinetic energy, total kinetic energy. We performed a Fourier transform, and we analyzed the frequency contained in the kinetic energy, in the variation of the kinetic energy in time. What we observe is that we have the frequencies from all the phonons, especially the sliding phonons, and other frequencies coming from the recombination. So there can be sum or differences of frequencies and other higher order effects. Then we said, OK, there is a first signature of the scattering. Then we performed a wavelet transform, which resolves in time the frequencies. So in the x-axis, I have the time of the simulation. In the y-axis, I have the frequency. The color means that the brighter it is, the more present is that frequency in the contribution of the kinetic energy, which means that we can clearly see that the spectrogram is split into 2 parts. The first one is when the sliding motion is active. The second is when it's over. In fact, when the sliding motion is active, we have the frequencies from the sliding phonons plus the frequencies from the scattering. Once the sliding is over, in fact, the scattering is less evident, is still occurring, because maybe the structure tries to slide, but it doesn't. And also we have some sliding phonons still active, but the energy is not enough anymore, as you can appreciate from the colors, it's not enough anymore to have a net sliding. The same can be obtained by analyzing the force on just the top layer. And yeah, here it's more evident that there are regions in which the force is more active, especially when it tries to slide, but the sliding is not possible at this moment. So the friction force basically is the sum of all the forces which activate this sliding process, the dissipative processes, sorry. We then applied this kind of analysis to the atomic force microscopy signals of a similar on the same material. This work has been done in collaboration with the Institute of Physics from the Academy of Science. And this is the wavelet transform of the FM signal. And we recognize the same pattern, the same sliding frequencies and recombination frequencies due to the dissipation processes, which we reproduced also in another simulation. Here, in the x-axis, I have the sliding distance. It's in white. I hope it's visible. Or the sliding time, which is the same because the velocity was kept constant in that experiment. Also, this analysis, the same year we published the paper, was applied by another group in the presence of electric field. So it looks like that maybe it's useful already for other people. Then I have a collaboration with Professor Carlos Figueroa from Universidad of Caxias do Sul in Brazil, in which they performed the experiment of silicon tip on titanium oxide. They observed that in darkness, they have a certain level of friction force. If the surface, the system, is exposed to the UV light, the friction decreases by 60%. We applied the same kind of analysis, and we realized with this kind of analysis that this most probably is due to the electron-phonon coupling. So how the energy is transferred from, how actually the electronic density is modulated by the UV light, and then this modulation is transferred into the interatomic forces and then to the phonon motion. So for a complete description, we have to include also the phonon-phonon scattering in our description. What's the probability that this dissipation occurs? We have two ingredients. There is the phonon population, which means how active are both sliding phonons and dissipative phonons, and the characteristics of the system. This is the dissipation channel. This is a scattering tensor. In general, the dissipation, I mean the recombination occurs among several phonons, the sliding plus n phonons, p phonons. Still, the ingredients are the same. So we have interatomic force constants, which can be parameterized, I mean, calculated by means of quantum mechanics. And we can proceed in a similar way. Either we control temperature, pressure, velocity, or other external stimuli to control the population, or to design a material, so something which is independent of n, we control phi. So either we proceed as before, as we did for omega, relating it to electrodynamical descriptors, or we can apply the phonon-phonon scattering rules, which I derived, not just for this system, but in general, based on the symmetries of the eigenvectors, the symmetries of these displacements. So in advance, without any need to compute all these elements, I mean, to evaluate and calculate all these elements, it's possible to know if a scattering channel, a dissipation channel is allowed, I mean, it's turned on or off. So there is no need to compute omega if we exploit the scattering rules. And this is another guideline for the design. We can act on the symmetries. Just modify locally the geometry. Then we start to distort, impose some permanent distortions by means of strains or other means like cation substitution. And we can act on the dissipation channels, turning them on or off. So this is the workflow, design a new material. First, we identify the sliding phonons. We do scalar projections. We see which are the displacements relative to the composing the total sliding. Then we find the relation between the frequency and other descriptors, collective descriptors, to not being lost into fragmentation. Then we control the dissipation channels. We act accordingly, according to this finding, by selecting some new geometry or modifying an existing one, and also the atomic type, and act with other fields, external stimuli, electric, electromagnetic, and so on. So the summary of my work is maybe this can be a path towards a universal description of friction and energy dissipation, because of thanks to its generality. There is no specific simulation or experiments that you have to do to parameterize specifically that specific equation for that kind of situation. So this applies in general. This saves effort, resources, and time. Includes naturally the quantum mechanics. So we don't need to make another effort to include the quantum description. Provides guidelines for material design together with these general findings, I mean, this general descriptor, the cophonicity, and the scattering rules. And being a general framework, it can be exploited for applications beyond tribology, for layer exfoliation, to design the heat transfer, the directional heat transfer, or exploiting the electron-phonon coupling for metal-insulatrons transition, or non-linear and non-linear optical response, and so on. Future plan of the work is to define the coefficient of friction from only the atomic type and geometry of the system. And the plan is to do it with some PhD students, one of the actual PhD students. Also to, other parallel fields, study photovoltaics, triboelectric nanogenerators, which is in progress within this CTU Global postdoc, which I'm mentoring, and I will involve also other PhD students. Photocatalysis for water splitting, which is already ongoing with the actual PhD student, and with a future global postdoc, which I will mentor starting from October. And finally, the other parallel goal is to extend and develop the framework and the software for normal dynamics. This is a new way to perform simulations, molecular dynamic simulations. Instead of solving the Newton equation, we will solve in the standard way. We can solve it in the reciprocal space, like in terms of phonon coordinates instead. The software is already available, and the papers, both, we sent joint papers, PRL, PRB, and both are under review in this moment. So let's see. Okay, this is the brief characteristics which we will discuss. So thanks a lot for your attention.
Thank you. Okay, so thank you for the nice lecture. And questions about the talk? Pavel Rybka.
At the beginning, in the motivation part, you mentioned planetary friction. Mm-hmm. And you, if I remember well, you referred to gravitational force between planets. So what is the relation between planetary friction and gravitational force? Would the friction be there, be existing without interplanetary matter?
I don't know if you really refer to something. Okay, taking the question as it is, if I understand correctly, yes, if there are no objects, there is no interaction, there is no friction. So if we have planets, we focus on just one planet which is traveling, others exert their own gravitational force, so they try to grab the planet behind. So this is a force, this is a friction force in general. Then, of course, the planet stops also for other reasons. There is some impact, so the transfer of kinetic energy directly, but in general, yes, if there is an interaction that grabs something, then it's friction.
Okay, so the friction needs the interplanetary matter.
Needs interactions. Without interactions, there is whatever, if it's matter or not.
So my question was if it needs interaction with other planets, because you mentioned gravitational force.
It can be also just with the fields, but I mean, this is larger.
So what is the relation between gravitational force and planet friction? That was my question.
Between the gravitational force and the...
Because you mentioned gravitational force.
Yeah, and this is...
So is it necessary for friction? Would it be, I mean, if other planets are absent, there would be no friction?
As if just the planet is alone, there is nothing else here, there is no friction.
Planet and interplanetary matter.
No, okay, if there is other matter, yes, there are interactions, then there will be friction.
Okay, so if there is a planet and interplanetary matter and other planet, does the other planet has any effect on the friction?
Yeah, sure. Because it's part of the gravitational force. Depends, of course, depends on the alignment, depends. There is also the tidal effect, for example. I mean, it really depends on the geometry, because they can even accelerate, actually, the system. This is something that happens, for example, for satellites that is exploited. We have the Earth, so we throw the satellite, and then we want to accelerate it. There is another planet, so that the trajectory is designed in such a way that it goes there. So in this case, it's accelerating and not, it's not exerting friction, but again, it depends, of course, on the geometry of the system.
Okay, so seems there are no... Oh, there, Pavel has a question.
Hello, thank you very much for a nice lecture. Well, I have a following question. I guess, well, your simulation and your model is quite complex, and you need a lot of parameters for your models. How do you verify that your models and your approach is correct? So if you use different materials, do you have some experiment which can predict, or if you have some case studies of materials which are really distinct, so which have no friction at all, that on which you prove that your approach and your results of your simulation are correct? So,
okay.
So what's a verification of your? Yeah.
So, related to the first part of the question, there is no specific parameterization, first of all. So I just need to know what are the atoms and where they are, which kind of atoms I have, because everything is included in the quantum description. So, and the formalism, again, is general. It's based on the second-order derivative of the, on the derivative of the potential. So you have the second order, which is the harmonic part, and then other anharmonic terms. So, but these, again, are general. And I can calculate it by means of quantum mechanics, which means it's not specific of the geometry and on the atomic type. This is one thing. Then, how do I verify it? We have already some examples. I mentioned these experiments like with photofriction in collaboration with Cachier-Sosul, in which, this is, with this kind of analysis, we already really see that it's about sliding phonons and how they interact. And also, okay, this is from our first paper about the complete story about the phonon scattering, in which we have an AFM atomic force microscopy signal evidence of this. And now it starts to be present also in other papers. So how do I verify the theory? These are just the first examples. It's relatively new. Let's say people need time to accept and try if they want, because maybe they have other ideas, of course.
Okay, thank you.
Joseph Kittler.
Thank you very much for a fascinating lecture. One of the reviewers referred to your approach as a static approach. Do you, and he considered whether one needs to actually apply an alternative involving dynamic simulation. Do you agree with his comment? Is what you are doing a starting point to be extended?
Yeah, sure. For sure, there are limitations. I think it's at the beginning, let's say, because how to evaluate these terms? These are evaluated statically. That's actually one of the main goals of the formalism, to avoid dynamic simulations. The idea is, let's see if it's possible to avoid this, because, as I showed after, everything is included here. So instead of doing dynamic simulations, we can do simulations by changing the phonon populations, for example, and calibrate. It's kind of complicated, and by now there is no software doing it, but it's not the difficult actually thing to design it. But we can recast this, the simulations on friction in terms of simulations on the phonon populations. This is one thing. That's actually one of the main goals, just to avoid dynamical simulations. From static properties, extract dynamical properties. It's true that these terms, they are constant within a certain extent. If I imagine that I destroy the geometry, not destroy, okay, but I deform the geometry a lot, then this does not hold anymore. But we can, I already was thinking how to extend the theory, because we get the phonons from the dynamical equation for the eigenvector equation by evaluating the derivative with respect to the position of this. So I can take it out, and anyway, I will get some expression of this, which depends on the dynamical matrix and then on the force constants. So I already have some idea, but it's still at the beginning, this part.
Thank you.
Okay.
Thank you very much for a very nice lecture. I learned a lot. So if I understand it correctly, like everything is governed by the quantum physics. So if you had a powerful computer, you could, in theory, simulate everything and calculate the friction exactly. But this is probably too hard, I assume. So you have a simplified formula, simplified theory, which predicts the friction in a computationally easier way. And my question is, are there any alternatives? Are there other theories which would give also predictions of frictions? And how do they compare to your work? Has there been any experimental comparison, for example? Thank you.
Yeah, the theories are, okay, apart what I showed, very old and general, really, they are phenomenological. Some, the only attempt that I saw going towards this direction with the phonon is from Professor Manini. This attempt has been done by considering just one linear chain of equal masses connected by an ideal spring. And with some tip, also modeled as an ideal spring sliding on top. But the phonons are just mentioned as a possible way of dissipation. But again, from this general description, they again get some formulation which is specific of the system. So anyway, there is something which is derived, which depends on some coefficient, which must be fitted to experimental data. So there is no attempt, as far as I know at least, but I read a lot really. And there is no attempt to study friction in this way. Concerning the supercomputers, yes, actually, this is a way to avoid to use, okay, still, it's true that to evaluate these terms, you still need quite enough computational power, but you can do a non-local cluster, like is the Research for Computer Informatics that we have here at FEL, which is not the IT for Innovation in Ostrava, which is much larger, but still with that cluster, we can do this kind of simulations, and we don't need long dynamical simulations ab initio.
And without phonons, are there some approaches without phonons?
Sorry?
Without the phonons?
Like other theories without phonons. Yeah, sure. What I just showed, like these phenomenological ones.
Okay, the very simple ones.
Yeah, simple or even with more complicated expressions, but still containing coefficients which must be fitted from experiments.
Okay, thank you very much for your nice presentation. I would like to ask about one mathematical aspects of your talk. You mentioned application of wavelet analysis. This is a whole variety. If you are doing wavelet analysis, you can choose or select various kinds of wavelets. So I would like to ask you, I wonder, what specifics wavelet package are you using?
The complex Morley.
Conflicts, that seems to be the most popular. Always I get the answer conflicts.
Complex Morley.
Conflicts. Yeah. Okay, thank you very much.
This one.
Okay, so I have one more question. This is related to the title, Universal Framework. Did I get it right that this is for crystallic? So if you have polymers or things like that, nothing of this is applicable?
No, it's applicable. Everything works because this is the phonon theory works also for molecules because it doesn't matter. It's all about what's the point in the reciprocal space that we consider. In the case of non-periodic system, just the gamma point. Actually, it's much easier. We don't need to stress about all. To consider also other both Q points and different J modes within the Q point. So if we just select this equal to gamma, that's a non-periodic system. So it's still valid.
Do you have any verified results with that?
No, I didn't. I was focusing just on the periodic structures because these 2D materials are those that are one of the main topic of our experimental part of the group.
Professor Wobecki had a question.
I would be curious. Could you imagine that you could simulate how to move atoms? Because it's my practical problems during friction that we have two materials, we load them thermally and they are sliding, and the atoms start to move and there is transfer of material. I know it's tricky, but just your opinion.
If I can you repeat the question? Like if I can simulate, like with this approach?
Yeah, or similar, or if you can imagine to formulate a model for this. Or
this is what is usually done in dynamic simulations. You have, if I understood correctly the question, You have atoms. I mean, you in your simulation, you set the geometry, so you put the atoms somewhere, you set the interactions, and you run the simulations. And according to what's the experimental condition that you want to simulate, so you apply some pressure, so some dragging force, for example, like in an AFM experiment, or some electromagnetic field, whatever. I mean, everything can be included in the simulation. The question is the size of the system, which is another problem of these kind of simulations, because the larger the system, the better the model. But the larger the system, the more unfeasible is the calculation, because we need more and more computation. That's the idea to avoid this kind of problem. Also, because the reciprocal scheme here, I'm going into maybe too much technical detail, but the reciprocal scheme that makes use of the reciprocal space, like for wave vector which are of the kind like 1, 4, 0, 0. This represents a 4 by 1 by 1 replica. So by selecting just specific Q points, I'm already considering the long-range interactions which I would need to include in a very large cell for a standard simulation. So this is another hidden aspect, but I didn't want to discuss this part. I mean, but of course, we can now, if you...
Okay, thank you.
Okay. Okay, Daniel has a question. Professor Clear in front.
Actually, just a little comment. This is one of the main aspects, the main point of this software that, I mean, this framework of normal dynamic simulation that I'm developing with my colleague Paolo Nicolini. Actually, exactly this one.
So I have one specific question. So in your simulation, when you have two layers interacting between each other, so how many atoms and molecules do you usually simulate?
For that system, if we exploit this, I have just 6 atoms.
Okay.
Just 6, because I have it's a bilayer. Okay, you can do it in bulk or just isolated bilayer, but the unit cell is this one. See, sulfur, molybdenum, sulfur. That's it, and then it's periodic.
So and how long it takes to compute everything?
All the phones, all this machinery, like I mean, if you have 64 cores, considering that for 6 you have 6 times 3 times 2, this is the number of single point calculations. It's about 2 days. You get all the first constant plus you have this to the square for the third order. Basically, in 2 days, yes, you get everything.
Okay. I will ask a question which I thought Professor Obecki asked, and I thought about transfer of atoms. So sometimes transfer of atoms. So if you slide something like something soft over something hard, it will deposit atoms on the other surface.
It's where, yeah.
And I think this was not considered at all.
This is considered in the next step. This is considered here. Because that's too much. You are breaking the structure. So yes, I have this. It's hard. Okay, in principle, if you take all of these terms, very, very high order, in principle, everything is there. Because this comes from the Taylor's theorem. So this is exactly defined everywhere. But then if you start to truncate, then it's over. So in that case, yes, of course, we have to include this variation.
So maybe the input would be 2 surfaces and the output would be how many molecules or atoms were deposited from one side to the other because of the friction?
In fact, I said towards a universal framework. I didn't provide the final answer yet. Okay. But this, I believe that this is the next step.
Thank you. One more question, Professor Hadra.
Well, I have one more question. As I see, your cluster is quite small.
Yeah.
Yeah, so usually you need to have a bigger clusters to get some to get a precise results in initial calculation. Usually in the semiconductors or in the semiconductor defects, we are using much more bigger clusters, and a careful normalization and the comparison with experimental data has to be done to fit it and to correct the simulate it virtual reality to in apostrophe reality. So do you think that, well, this size of the cluster is appropriate for
No, if you have
to describe the whole process? Yeah.
No, this is a pure system. If you have defects, no, this is not enough, for sure. You have to expand it to include the defect, and the size must be consistent with the concentration of the defect. I mean, the size must reproduce the concentration of the defect, for sure. I mean, this cannot make miracles, okay? So you have to include the defect, but still, if you want to consider long-range interactions, okay, your system is already big because you have the defect, vacancy, another dislocation, whatever. This is big, but then you can apply this for longer interactions, considering other replicas. You don't need this supercell. With the standard approach, yes, but with this one, no. And this is what I was commenting before, because you can include in the description, in the scattering, suitable reciprocal points, which represent suitable replicas of the system. So in that case, yes, you can save a lot of time in the case of long-range interactions, but for the defects, no, you have to build the system. And concerning your comment about the parametrization, of course, even if it's ab initio, it's a model. I mean, if we want to reproduce some experiment, we want to understand what's going on in the experiments, we don't see the atoms. So, of course, we have to consider different unit cells with different concentration, but this is out of this formulation. This comes before. This is about the reliability of your model. So this is independent.
Okay, thank you.
Your speech is interesting, so we are piling up the questions. Yeah? So basically, you could develop models, yeah, and input them to some macroscopic simulators to,
yeah,
which would be helpful. So you don't need to simulate in big scale, but you could generate the fermat. Okay.
Yeah. This can be easily integrated with high throughput machinery, actually, and also with these databases for machine learning, for example.
So if we need some constellation, we can come to you and ask, do for us this and
hopefully,
that.
Yes.
Thank you.
Okay, so it seems there are no more questions. So thank you again. This concludes the proceedings in this room. In 5 minutes, we continue still with the public part. It will be in room 80, and it's important that the members of the committee, and if the reviewers are here, which are not, go please to room 80 where we still continue and we need your help.